Hey everyone, this is our day on solving systems of linear equations, the third and final day for our Unit 1. So after this will be our unit test. So let me get my pen working. Also slightly different compared to what I've been doing. I am pre-recording this video for the week, so you will be able to have it no matter what day prior to that. Prior to the day you have notes in class. So that said, I might change things up as we get to class based on this video, so we'll see. All right, so let's get into it. First of all, let's go over a quick warm-up from the writing equations that we did during the last lesson. So write linear equations with the given information below. Given the point 4, -3, and slope of 5. So given a point and a slope, we jump straight to point-slope format or formula to get our slope-intercept form. So 5 on the outside, x minus 4 minus 3. So the x changes, the y does not. Distribute the 5, 5x minus 20 minus 3, 5x minus 23. Okay, remember the goal or the strategy is always point-slope form, and then the goal is always y equals mx plus b. Number 2, given the points 2, 6 and -1, 3. So this is a 2-point problem, which means you're given 2 points. You need the slope first. So let's see, 6 minus 3 on top, 2 plus 1 on bottom. I get 3 over 3, which is 1. I'm going to choose that point because there's no negatives. So 1 on the outside for the slope, x minus 2 plus 6, distribute the 1, and x plus 4. And lastly, given the point 5, 9, and perpendicular to y equals 5x plus 2. So first of all, the m is going to be our slope. So if the original is 5, the new one is -1/5. And I don't need the equation after that. Y equals -1/5, x minus 5 plus 9. Distribute the -1/5. -1/5 times -5 is +1. So -1/5 x plus 10 is our answer there. All right. So moving on. So first question, what is a system of equations and what does it mean to solve one? So a system of equations is a group of equations that somehow work together. So in a business, you could have profit, loss, expenses, all kinds of equations that work together. The solution to a system of equations is the point or points that solve them all simultaneously. On a graph, it is the point where the lines cross. So let's say we have some equation, y equals blah, 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 and another equation, y equals blah, 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 blah. Oftentimes, you'll have a system like this connected with a little squiggly bracket, sometimes, just to kind of tell you that it is a system. A system can have thousands of equations, thousands of variables. Okay, for the most part, we're just going to have 2 equations, and they are linear, so x, y. If these were to be graphed, so let me change my color for the other lines. Let's say we have one right here and one right there. The point where they cross would be the solution. And it always is written as an x-y pair. Okay. So on the graph, it's where they cross. Now, graphing is one of the primary methods to solve them. Okay, and we'll talk about that one first. Now, how many solutions can there be? There can be a no solution. No solution happens when the lines do not cross, or if you have tons of lines, maybe they all don't cross at the same place. So then there would be no solution. One solution, the lines cross once. The most a linear system can have. Okay, because if you think about it, lines can only cross each other once. 2 solutions, the lines cross twice, etc. Infinite solutions, the lines are the same line. So, of our linear equation systems, it's only going to be one of those 3 options. There's either no solution, one solution, or infinite. Now, if you do have a solution, it is a coordinate pair, so there are two numbers involved, okay, an x-y combination. That does not mean there's two solutions. It is one solution. It is a location that requires both an x and a y. Now, solve by graphing. It's really only convenient if the intersection is whole numbers, or if you have a graphing calculator or can use Desmos. So the example here, number 1, we have our graphed lines. Our solution would be 1, 3. That's the solution of the system. So the steps: rewrite the equations into an easier form if needed, graph all the equations on the same graph, find and state the intersection if it exists as a coordinate pair. So I'm going to go ahead and use Desmos to kind of show you how this works. And by all means, feel free to use Desmos when you're working on the stuff at home. Just don't get too used to using it. Don't use it as a crutch because you can't use Desmos on the test. But here's going to be our first systems. Y equals 5x minus 3, y equals negative 2x plus 4. So 5x minus 3 and negative 2x plus 4 on Desmos. 5x plus 3 and negative 2x plus 4. And Desmos does a great job of giving us an answer right there. Let's see, did I do that right? 5x minus 3. Sorry, I wrote plus 3. All right, that's a better answer. So our solution is 1, 2. So Desmos can give you the answer in a very short amount of time. Okay. It can even give you the answer when they are not written in slope-intercept form. So x plus 3 equals y. And negative 16 minus 3x equals 4y. Let's see, did I type that in right? Oops, what happened up here? Hold on a second. X plus 3 equals y. There we go. So I forgot to erase the whole first one first. All right, so the solution here is negative 4, negative 1. Okay, so pretty basic if you can use Desmos. However, on the test, you will not be able to use Desmos in class. So make sure you have other strategies to go about using it. Now, when you're solving a system of equations, I generally don't care what strategy you use. In this lesson, I will go over all 4 strategies. Graphing doesn't have to be the one you use. It can be the one you check your answers with, if you have Desmos or a graphing calculator, but it doesn't have to be the one you use. Now, let's talk about another strategy, setting equal. Only convenient when both equations are already in y equals or x equal forms. Set the equations equal to each other and solve for the remaining variable. Plug your number into either original equation and solve for the last variable. State your answer if it exists as a coordinate pair. So this number 3 is going to show up as the final step of all of these. Okay, make sure you state it in a coordinate pair. So set the equations equal to each other and solve for the remaining variable. That's the tricky part. You always need to make sure you solve for both numbers or else you only have half a solution. So let's try a couple of these. So the system, both the equations are in y equals. So what I can do is I can jump straight to saying 5x minus 3 equals negative 2x plus 4. Okay, if they're both equal y, I can set them equal to each other. Solve for x, so I'm going to add 2x over here, add 3 over there, divide by 7, x equals 1. That's half my answer. I'm going to take that and I'm going to plug it into one of these, doesn't matter which. So 5 times 1 minus 3, 5 minus 3 is 2. So y equals 2. So my answer is 1, 2. Let's check that on Desmos just to make sure. 5x minus 3 and negative 2x plus 4. Oops. And I get 1, 2. All right, next one. They're both y equals, so negative 2x minus 4 equals 4x plus 2. Add 2x, let's do minus 4x over here, so negative 6x. Add 4 over there, so 6, divide by negative 6. X equals negative 1. Take it and plug it in somewhere. Let's plug it in there. 4 times negative 1 plus 2 is negative 4 plus 2 is negative 2. So y is negative 2, which makes my answer negative 1, negative 2. And we can check that on Desmos as well. Okay, so you'll notice that each of these strategies involves a different type of skill. Like I said, I'm never really gonna care which one you use, so long as you're at least competent in one of them. However, sometimes problems will be easier done in one strategy versus another. Sometimes they're set up to be graphed. Sometimes they're set up to be set equal, or the other two that we're going to do. So it really doesn't matter which one you choose. However, some of them might be easier on certain problems if you're good at that strategy. Okay, so let's look at an example of what happens when there are infinite or no solutions. Okay, so remember you can have one solution, infinite, or none. So let's see what happens when I do set equal. So these are both y equals. So I can say 5/3 x minus 4 equals 5/3 x plus 3. I don't like that fraction, so I'm going to distribute a 3 and get rid of them. Cancel, cancel. So I get 5x minus 12 equals 5x plus 9. Minus 5x minus 5x. Negative 12 equals 9. Well, that's not true. That means there is no solution. My x's disappeared. That's not good. So that's one example about how things can go bad. Okay, if your variables disappear and you're left with a number and another number that are not equal, then it's illogical, no solution. In this next one, well, first of all, it's not set up very nicely. So we're going to rearrange it a little bit. So negative 4 equals negative 2x minus y. I'm going to move the negative 2x over. So 2x minus 4 equals negative y. Divide by negative 1. Negative 2x plus 4 equals y. The other one is almost there. If I move the 4 over, I get y equals negative 2x plus 4. Would you look at that? Those are the same equation. Same equation means infinite solutions. Because they are the same line, they will overlap. Infinite places. Okay. So if you get something where, it's a number that doesn't equal another number, that's no solution. If you get something where they are equal, then infinite solutions. If I try to set those equal to each other, I'm just going to wind up with like 0 equals 0. So, all right. Substitution is a very algebraic way to solve things. Okay, so only convenient if one or both equations is already solved for a variable. The steps are very similar. Plug the solved equation into the other, then solve for the remaining variable. If needed, plug the first variable solution into the first equation and solve. And just like all the strategies, state your answer if it exists as a coordinate pair. And a note down here, set equal is a form of substitution. So we've already been doing substitution. Now, substitution is usually the type of problem that people avoid, just because it's more algebraic. But depends on the person, so we're going to go over it. So let's check these out. This first one of them is set as y equals. And so what we're going to do is we're going to take that entire equation and shove it right there. Substitute it. So negative 5x minus, and then in parentheses, negative 5x minus 7 equals 7. So I've got, let's see, negative 5x, let's see, double negative, plus 5x plus 7 equals 7. Oh, 7 equals 7. What that means is it is an infinite solution. problem, because those would cancel and I'd have 0 equals 0. So make sure when you know it's an infinite solution, you stop there. Don't try and go further. Okay, same as if it was a no solution problem. Don't try to go further. Okay, stop and leave it as is. This next one, it is not set up for substitution yet because there is no variable alone. However, I see a variable without a coefficient, so that will be easy to solve for. X equals negative 4y minus 2. Move the 4y over. So what I'm going to do is I'm going to take this and plug it into the other equation right there. Negative 4 parentheses negative 4y minus 2 minus 2y equals negative 6. Do a lot of distribution. 16y plus 8 minus 2y equals negative 6. Let's see, combine the y's. 14y minus 8 from over there, negative 14. So y equals negative 1. Half my answer. I then take that and I plug it into the other equation, the one I have not used yet for a plugin. So x plus 4 times negative 1 equals negative 2. X minus 4 equals negative 2. X, let's see, add 4 to both sides, equals 2. So my answer, 2, negative 1. Okay, so substitution is a very algebraic way to solve. And some people shy away from that, and that's fine. Okay, definitely use Desmos, check your answers, okay, make sure you know you're right. Just don't use it as a crutch. Okay, use substitution if you want to. Okay, it's one of 4 methods. You have graphing, you have set equal, you have substitution, and then the next one. Okay, you don't have to use it. All right. Elimination is a nice handy trick that a lot of people like to use. And so let's go ahead and go into it. Now, if needed, multiply one or both equations by a number to set a variable up to be eliminated. Squish the equations down into one, eliminating one variable in the process, and solve for the remaining one, and then plug the solved variable into the other equation and solve. So we need to find the other number. And then, like all the methods, state your answer if it exists as a coordinate pair. So it's really convenient when they're both already set up like this, standard form. So here's a couple examples where they already are. And it looks like they're nice and lined up. We have x's on top of x's, we have y's on top of y's, we have numbers on top of numbers. Also, it's very handy we have a plus minus of the same one, which means as soon as I shove this down, I will eliminate the x, because negative 2 plus 2 cancels. Y plus 3y is 4y, 4 plus 28 is 32, divide by 4, y equals 8. I'm halfway done already. Okay, so elimination is a very nice trick. I'm going to plug that in right here. Negative 2x plus 8 equals 4, minus 8 from the other side, negative 4, divide by negative 2, I get 2. Now I'm done. 2, 8. So elimination is a very handy trick that can take away quite a bit of work from a substitution problem. Now, this next one is elimination as well. However, we have to do something first. So it is nicely set up. X's on x's, y's on y's, numbers on numbers. However, I don't have any plus minuses. I have a 12 and a 4 and a 1 and a 9. So what I can do is either turn the 4 into a 12 or the 1 into a 9. I'm going to take this whole bottom equation and multiply it by 3. So the first one is going to stay the same. Second equation is now going to become 12x minus 27y equals, let's see, 3 times 19 is 57. And let's see, did I do that right? 3 times 9 is 27, 3 times 19, yeah, 57. Okay, so when I condense these, squish them down, That cancels. Let's see, 1 minus 27 is negative 26y, and 21 and 57 become 78. Divide by negative 26, I get y equals negative 3, halfway done. Go back and plug it in. Negative 12x minus 3 equals 21, so negative 12x equals 24. Divide by negative 12, x is negative 2. Now I am done. So elimination is a very handy trick to squish things down, cancel out some of the work that you would otherwise have to do. All right, so let's look at what this might look like on a test question that's a word problem, where you have to create your own system of equations. Okay, so sometimes you have to create your own, and that's kind of worst case scenario. So, potential test question. The school that Ryan goes to is selling tickets to a choral performance. On the first day of ticket sales, the school sold 11 adult tickets and 6 student tickets for a total of $202. The school took in $124 on the second day by selling 2 adult tickets and 12 student tickets. Find the price of an adult ticket and the price of a student ticket. So hopefully it's kind of obvious our 2 variables are going to be adult tickets and student tickets. So I'm going to say x is adult, y is student. So in the first day, there were 11 adult and 6 student tickets, which earned us $202. In the second day, we sold 2 adult and 12 student and earned us $124. So now I have a system of equations that's almost set up for elimination. However, I don't have a plus minus of the same thing. But I can turn that 6 into a negative 12 by multiplying by negative 2. And let's see, that gives me negative 22x minus 12y equals negative 404. Other equation didn't change. Now when I shove stuff down, the y goes away. Negative 22 plus 2 is negative 20x. Negative 404 plus 124 is 280. Negative 280, I believe. Divide by negative 20, I get x equals 14. So adult tickets are $14. I'm going to go ahead and take this, plug it back into one of my equations. 2 times 14 plus 12y is 124. 28 plus 12y is 124. Minus 28. And I get 96. Divided by 12 is 8. So student tickets, $14, or sorry, adult tickets, 14, students, 8. So trickiest part here is setting up your own system, okay, and then you solve it as is. So you should probably expect a couple of those on our first test. So just make sure that you're good for that. All right, lastly, there are a few example problems that we are going to end class with. I'm not going to go through them all right this moment. I'll give the first few steps and, see if you can kind of go from there. Number 1 and number 2 are both, for me, set up either for graphing or for set equal because they're both sets of y equals. So, first step on number 1, 1 half x plus 4 equals negative x plus 1, and you can take it from there. Number 2, first step is 5 halves x plus 3 equals negative x minus 4, and you can take it from there. Number 3 and number 4 are both set up pretty decently for elimination because number 3, when I squish it down, the y's cancel, I get 2x equals 2, so x equals 1, already have one of the numbers. Take that, plug it in, finish it up from there. Number 4 is almost there, but I don't have a plus minus yet. I'm going to take this bottom one, multiply it by negative 1. Now I have 5x plus 4y equals 12, and negative x minus 4y equals 4. Squish it down, I get 4 x equals 16, so x equals 4, half the answer. Plug it in somewhere, and you're good. Okay, numbers 5 and 6 are way trickier setups. So I'm going to kind of let you take it from there and give those a try. The hint on how to start is the fact that it's not really set up for anything yet. You can set it up for elimination if you want. You can set it up for substitution. If you want to solve for some variables first, you can throw it on Desmos, graph it that way. But, just take some algebra to kind of set it up for what you want. So, as of the end of this lesson, that is it for Unit 1, which means we're essentially good to go for a test. So make sure you're doing what you need to do, asking questions, seeking help, trying all the problems and whatnot. So make sure you come to class with questions, and I'll see you at some point this week.